Hey kiddos, we're going to do a few demonstrations today. As you can see, we're going to talk about factors that affect the rate of a chemical reaction, and we're going to do these in the same order that we have them in your notes. The first factor will be the nature of reactants. I have a couple of ionic compounds here, sodium chromate and lead 2 nitrate, and they have been dissolved in water. So we have ions in solution. Now, ions in solution react at a very, very fast rate. We'll have the positive lead ions being attracted to the negative chromate ions, and that's an instantaneous reaction. So the type of reactants you're dealing with often determine the rate of the reaction. So let me add the lead 2 nitrate to the sodium chromate, and we'll see how quickly that reaction proceeds. And you can see that the yellow precipitate forms instantaneously. Okay, so nature of reactants is a factor that affects the rate of a reaction. So you can see the yellow precipitate there, and that will eventually settle out. Now, another factor I'd like to talk about would be the concentration of the reactant. So I have in these two beakers some zinc ingots. You can see those at the bottom. I believe I have 4 zinc ingots in each. And in this graduated cylinder here, I have some 6 molar hydrochloric acid that's quite concentrated. When I add the 6 molar hydrochloric acid to the zinc ingots, you'll see that the zinc begins to react and bubble and fizz and at a fairly fast rate. We are producing zinc chloride in solution and hydrogen gas. So you can take a look at that rate, just qualitatively observe how quickly the hydrochloric acid is reacting with those zinc ingots. Now, the next one, I'd like to perform a dilution. I have some 6 molar hydrochloric acid here, 10 milliliters, and some distilled water in this graduated cylinder. I'm going to add the 6 molar to my distilled water. Go ahead and stir that so it goes into solution. And then we are going to obtain 10 milliliters of that diluted acid this time. So we'll pour it into this 10 milliliter graduated cylinder and get about 10 mils. So the same volume that I used just a moment ago. And we'll add that to the zinc ingots. And we'll see how fast this reacts. So once again, here's the 6 molar reacting with the zinc ingots, and here is the 10-fold dilution. So this is 0.6 molar, and I imagine there's some reaction going on, but it's very, very slow. So the higher the concentration, the greater chance there will be for meaningful collisions between particles, and therefore the rate will increase. Okay, next up will be something called surface area. So in these 2 weighing boats, I have 3.17 grams of zinc ingots and 3.17 grams of zinc powder. Now to the beaker on the left, we'll be adding 10 milliliters of 6 molar hydrochloric acid, and also to the beaker to the right. So the hydrochloric acid concentration is the same and the volume is the same. Let's go ahead and see what happens when I add the ingots to the 6 molar. And as we saw just a moment ago, the rate is about the same. Now let's take a look at my zinc powder with the same concentration of hydrochloric acid. We'll see how quickly this reacts. So I'll add the powder, and you can see that as the surface area increases, there's a greater chance for collision between reacting particles, and so the rate is substantially faster. So that would be an increase in surface area, increasing the rate of a reaction. Next up will be temperature. So I have some water on my hot plate here. Temperature of this water looks like it's about close to 74, 75 degrees Celsius. And then I have some ice water, and that looks like that might be 5 or 6 degrees Celsius. Let's go ahead and We'll add some ice water to this beaker. Hopefully just water and not too much ice. Oh, we got a couple pieces in there. And let's add an Alka-Seltzer tablet to the ice water, and we'll see how quickly that reacts. So once again, we're doing this qualitatively. We're getting an idea as to how quickly that reacts with the cold water that's, what was that, about 5 to 8 degrees Celsius. Okay. What do you think is going to happen when I add an Alka-Seltzer tablet to my warm water? Let's take a look. Same size tablet in my warm water, and you can see that the tablet reacts considerably faster. So once again, the higher the temperature, the greater the kinetic energy of reacting particles, so the greater the chance for a meaningful collision. So temperature an increase in temperature will always speed up the rate of a reaction. So that Alka-Seltzer tablet has reacted, and this one here in the cold water is still slowly reacting, as you can see. Okay? All right. Next up will be the addition of a catalyst. Now you will learn that a catalyst reduces something called the activation energy of a reaction. So I have for you 30% hydrogen peroxide. It's very, very concentrated hydrogen peroxide. 10 milliliters I'll just pour into a beaker. And the hydrogen peroxide molecules actually react with each other to decompose, and they form water and oxygen gas. Now you can see that not much oxygen gas is being formed right there. It's a very, very slow rate because the activation energy is very, very high for this reaction. So if I could lower the activation energy, I can speed up the rate of that reaction. So let's go ahead and we'll add 10 milliliters of hydrogen peroxide to this second beaker again. And here I have some potassium iodide dissolved in water. So I have a homogeneous catalyst. The iodide ion catalyzes this reaction. It provides what's called an alternative pathway for this reaction to proceed, and it lowers the activation energy. So let's add the iodide ion to the hydrogen peroxide solution, and you can see that it reacts very, very quickly to decompose. We get the brown color there, and that brown color is the result of I2 being formed. But essentially it's the iodide ions that react, and there we go. The hydrogen peroxide is now completely decomposed to water and oxygen gas, while this one is still slowly reacting. It might take 10 or 15 years for that to eventually decompose without the catalyst. Okay? So we've talked about several things. We've talked about the nature of reactants. Talked about concentration. Remember 6 molar hydrochloric acid and 6/10 molar hydrochloric acid. You can see the relative rates there. We talked about surface area, and so we had zinc powder and the zinc ingots. And then temperature. Looks like this Alka-Seltzer tablet might finally be dissolved. This one has long been dissolved. We then talked about the use of a catalyst in lowering the activation energy of a reaction. So hope you enjoyed those demonstrations. Talk to you soon. Bye-bye.
This demonstration is a fun way of showing the effect of different catalysts on the rate of decomposition of hydrogen peroxide. Before moving on to the demonstration, it is important to establish for the students that hydrogen peroxide is indeed decomposing all the time, otherwise the students may confuse reactants with catalysts. One possible way of doing this is to show that the bottle of hydrogen peroxide is vented to allow oxygen to escape. Another way is by pointing out that the hydrogen peroxide is stored in a refrigerator and that it has a finite lifetime. Line up 6 large cylinders and add catalyst to them as follows. half a gram of manganese dioxide, half a gram of lead dioxide, half a gram of iron oxide, a small amount of chopped potato, a small amount of chopped liver, and a small amount of chopped boiled liver. It needs to be boiled in water for about 5 minutes. To each of these, add 1 centimetre cubed of washing up liquid. It doesn't need to be measured accurately, but you need to use the same amount each time to ensure that it's a fair test. Avoid spilling the washing up liquid down the sides of the tube. And indeed the catalyst also needs to be at the bottom of the tube and not down the sides. Then simultaneously add 25 centimetres cubed of 75 vol hydrogen peroxide to each of the cylinders. The foam will rise up the cylinders at widely differing rates. The foam is formed from oxygen, which is produced by the decomposition of the peroxide. The rates at which they rise up the cylinders give a graphic comparison of the differing effectiveness of the catalysts. The order is normally lead dioxide, manganese dioxide, fresh liver, potato, iron oxide, and then boiled liver, but this may be affected by the surface area of the powders. Liver contains a peroxidase enzyme which is denatured by boiling it. It is usually possible to light a glowing splint in the foam, although sometimes this fails if there's too much water in the foam. This demonstration can lead to plenty of discussion and possible further experimentation. Is it in fact a fair test? Should we be measuring the number of moles of each of the catalysts rather than the number of grams? How much of the potato and liver is actually enzyme? Are the surface areas of the powders comparable?
Copper ions react with sodium hydroxide to form a blue precipitate of copper 2 hydroxide. This precipitate does not dissolve in excess sodium hydroxide solution.